So, does anybody have any questions about the? Actually, any of you guys watch Holy Moly on television? Ever watch Holy Moly on television? You guys watch Wipeout? Yeah. So they took Wipeout and they added miniature golf. That's what Holy Moly is. I mean, for some reasons, I want to say either, I can't forget if it's Seth or Steph Curry. He's like in charge of this somehow. Right. Yeah, like that one, the famous basketball player. Yeah, they're both famous, but the more famous one, I believe. No offense, but I know him. Actually, I almost taught the less famous one. What's his name? Seth. I had Seth in Calculus 1 when I first started teaching at Liberty back in like ages ago. And he was in class one day. And all the other students were like, "Hey." I'm like, I don't know who he is. You know, I don't know anything. I don't follow anything. I'm like, to me, he was just the student who never responded to my emails for the next 3 weeks. Because shortly after that, he dropped out and went to Duke. Because it turns out it's better to play for Duke than to play for Liberty, right? I mean, come on, right? So, yeah. Anyway, that's the closest I've ever got to NBA royalty in my teaching. Anyway, this Holy Moly show, getting back to that, they had after the regular show is done, they have like a 2-part finale. So it's kind of inspired by that to split your final into 2 pieces, right? So we have like a best of and then a best of the best of show. But the first best of is before Thanksgiving, right? So final part 1, I think I put it, Tuesday before the Thanksgiving break? I think what I did, if I remember right. Anyway, it's in the announcements. It's there. Look at it. You need to be, studying, trying to go back to test 1. Even now, try to pick a day sometime with a tutor, with me, whatever, to go back, review through test 1 and see, like, what did I get wrong? Why did I get it wrong? What do I need to do to fix it so I don't lose those points again, right? Was it just carelessness, right? Could be that, right? Maybe I just need to be, maybe you just need to double check your answers, right? And that'll fix it for you. I mean, it could be a lot of different things. But I do want everyone in here to pass. In fact, I would like for everyone in here to make a solid good grade. You know, I mean, I would be completely fine with awarding everyone an A and a B, but you got to get to that like level of understanding. And so some of you have ways to go. I know some of you are just trying to pass because this is like your last math class, and I understand that too. But don't aim for a C, because if you aim for a C and then things go just a little bit sideways, all of a sudden you got a D, right? Which won't help you, probably. Would D work? It depends on your major. Like a lot of times you need a C in this course to get, at least where I was before, a lot of times people need a C in this kind of course in order for it to count. I don't know. Maybe a D will work for you. But even so, like, try for more. Like, you don't want that to hurt your GPA either, right? So try to aim for higher. And the way I have this course structured, like, nothing is set in stone yet, right? If you do better on the final, you will improve your grade if you do better than you did on the test, right? So there is, there's opportunity to improve. Anyway, so I hope the bonus quiz helped you in that direction. I think, so it doesn't hurt your grade, right? And so these points you got on the bonus quiz, these are points that you keep. I won't. I'm not lumping them into test 1. So if you dropped test 1 for the final exam, you'd still keep your bonus quiz points. All right. So they could help cover up, like, maybe you did something bad in the homework or something, like didn't do it. If you just didn't do the homework, oh, by the way, you have another day. You want to turn in now? I take that as a no. So, yes, that was announced. The news is still spreading. So I've been before you got in here, I was trying to trick students into thinking it was due today. So I originally did say it was due Tuesday, but I pushed it back a day because I looked at our course planner, and originally I only had like 1 day in this week, but there are 2 days in this week, right? So I don't know how my table got messed up. Okay, so is there a holiday? I hope not. Not to my knowledge. It's like there's a made-up holiday. So pretty much today, we can talk about Mission 3. There's one thing I should share with you, because I was talking to a student about graphing. And so one thing is, on the test, I'm not going to force the issue of like transformations of graphs. I might just ask you to graph something, and I won't like pin you down to one method. So if you want to use a graphing calculator, if you want to plot points, that will also be a legitimate method. You won't necessarily have to do like, there's one problem in the homework where I've actually asked you to go through steps of transforming a function to another one, through like shifting and flipping over and stuff like that. I won't force that on the test. So on the test, like if there's a graphing problem like that, you could just use whatever method suits you. If you like the transformation, starting with the basic one and shifting it around, that's fine. But I won't force that. In contrast, like completing the square, that's something that I'm, requiring you to learn. Although I don't know if that is super relevant to test 2. Maybe not. But would completing the square be on the final? Yes. Like, yeah, I'm pretty sure it will be there. Okay, so what I wanted to share with you was a sort of quick guide to graph something of the form y equals ax squared plus bx plus c. All right. In other words, so we already have a definition for a line, right? We defined lines in here, didn't we? I think we did. Let me define sort of the analog of the point slope formula for a parabola. So here's the definition. If y is equal to k plus a times x minus h quantity squared, then this is a parabola with vertex h comma k and axis of symmetry x equals to h. Moreover, there are 2 cases, all right? What are the 2 cases? Either the parabola opens up or the parabola opens down, right? So case number 1, let's suppose the a is greater than 0, then it opens up, right? So it looks something like wherever that vertex is, right? And then it kind of like that, right? Now, of course, the vertex doesn't have to be in quadrant 1. It could be anywhere, right? That h comma k, it could be anywhere, that vertex. I'm just drawing it in quadrant 1 for the sake of artistry. Next time I'll put the vertex somewhere else. If a is less than 0, that vertex could be anywhere. It could be here, for example. And if a is less than 0, then the parabola, it opens down, right? What can we say about the vertex of the parabola in both cases? It's a example of a local either minimum or maximum. Yeah. In fact, we could even say more, right? It's a global minimum maximum for this particular example. So And I mean, how could you make these graphs better for a given quadratic? Like you could figure out where the y-intercept is. What will the y-intercept be? I guess what I'm asking is, in terms of the formulas which are on the board, what is it? I mean, it's not easy to see what it is in the HK formula. But this one up here, what's the y-intercept if we look at that formula? C, right? So if you have it in that format, it's easy to see that the y-intercept is at C. The y-intercept in here, you'd actually have to kind of like, you'd have to plug it in. I mean, if we say f of x is equal to k plus a times x minus h squared, call that the function, that's a quadratic function. F of 0 would be equal to the k plus a h squared for what it's worth. I mean, there's the formula for it, but no, you don't need to memorize that or use that. I don't recommend it. What you should do for a specific example is just plug in 0 and see what happens, all right? But you guys do get a formula sheet, right? So I would urge you, forget about what's in the green here, but what's in the blue, like that would be good to have on the formula sheet so you know, hey, if I have a quadratic, if I can make it look like this, I can quickly graph it, right? At least I can, I can have I can make a quick sketch of it without, too much work. For example, if I had y equals to 4 plus x minus 3 squared, I can graph that very, I said axis of symmetry. I forgot to draw that on those graphs. Where is the axis of symmetry? I'll make it red. Yeah, where the vertex is? But it's like a vertical line through that, right? So like that. If I made my graph right, you'd see that the parabola is like reflected across that line, right? It should be symmetric across that vertical line. So this is a parabola, right? Where's the vertex?
Vertex is at -3, 4, right?
Uh-huh. Open up or down?
It's opening down. Wait,
Up, yeah. So that's pretty much all I need to make a quick sketch of it. 1, 2, 3, 1, 2, 3, 4. So it's like here, right? And that thing opens up like that. And I failed. I mean, this isn't wrong, but this is poor planning on my part, right? Let me make that a little bit lower. Let's see, 1. Can you tell me what the y-intercept would be? If I call this f of x, what's f of 0? What is f of 0 there? Plug in 0, right? We get what? 4 plus what? 0 minus 3 quantity squared, which is what? Minus 3 squared is 9. 4 plus 9? 13. So this has a y-intercept of 13. It's kind of about like up here. Right? So if I have that point and I have the vertex, and I know that that's the vertex, that pretty much is all I need to graph the parabola somewhat carefully. I mean, you could add another point to make it prettier, but roughly speaking, it's something like that. right? There you go. Now, what if our formula doesn't come prepackaged all nice and pretty like that? Like, what if instead of that we had something like y equals to, x squared plus 8x plus 2?
Put it in the other form.
Right, and how do we do that?
Complete square.
Complete the square, that's right. So that's why I was probably hedging a little bit on whether or not completing the square was on test 2, because maybe it is, maybe you want to do this, That's x plus 4 squared, which means I've added 16, which means I need to subtract 16, right, plus 2. See? You guys are getting it. That is minus 14. I'm not sure what was just said, but I'm going to assume it was not extolling the joys of learning mathematics properly. Let's see. X plus 4 squared. Now we can read what's the vertex, yeah? Vertex is where? -4, -14, right? And it opens up, so I'll draw it up here. So -4, I mean, it's like down here somewhere, I don't know. And the y-intercept is easier to see this time because it's 2. So roughly speaking, something like that. So if you understand this formula, you can sketch a quadratic pretty fast. Now you were like, well, I could just do the same by plugging in 3 points and being careful. Sure, I'm not against it. If you want to plug 4 points into the graph and create the graph that way, or use a graphing calculator, I'm also fine with that. I'm just not teaching it, okay? Don't be confused if there's not an h. This will sometimes get students confused. Like, what if I had y equals to, 3 minus x squared? Where's the vertex in this case? Zero, 3. Very good. Yeah. And it opens what? It opens down. So here's the vertex. Right? Opens, and the vertex is the y-intercept in this case, isn't it? So what else could we do? We could figure out x-intercepts, couldn't we? We could factor this thing. This is what? Square root of 3 minus x times the square root of 3 plus x, using the difference of squares. And so like the x-intercepts here are plus or minus where? Well, plus or minus the square root of 3, right? What is that? Yeah, 1.7-ish, something like that. So it's about a little bit more than halfway there. So roughly speaking, it could be like here and here. So here's a kind of a good sketch. Now I'm not always that. If you watched me making quick graphs in here, I'm not always that careful, right? Sometimes I just need a sort of a sense of what the thing looks like. It depends on the question. One of your homework problems is about finding maximums and minimums, right? So there you don't need a super careful graph. You just kind of need a gross picture of what happens, right? Let me show you an example kind of like that problem, but more complicated. So this thing I just showed you, I don't think it necessarily helps with the homework that I've assigned you directly, but I think it's likely on the test that one of the questions is graph a parabola, right? And so up to this point, the way you would have done that is with the transformations of graphs or with just plugging in points. So now I've given you another way, right? And I think it's, I mean, these are things that should be said in this course at some point, and so now I've said them. All right, so let's look at how many local min, local max, sketch graph for y equals to, let's say, x plus 6 squared times x plus 3 times x minus 2 times x minus 4 squared and times x minus 8. That should be enough. All right, so if we're going to graph, you're like, oh, that's kind of scary, but don't be scared. This is actually very simple. So we're graphing a polynomial, and the formula is completely factored. Just like your homework problem. I gave you a formula which is completely factored, right? So you can see when that's 0, right? What's the graphical significance of that being 0? What does that tell you? What? X-intercepts, right? And when is this 0? Can you tell me? For what x?
For x equals -2.
I got a minus 6.
-3, +2, 4,
And 8, right. These are what I've called algebraic critical numbers when we were studying like that inequality problem, right? So here I'm just kind of taking the next step and saying, you know what, we could actually make a picture of the graph rather than just drawing a number line. You know, that's kind of the next step, if you like. And so those are the places where the graph can cross from positive to negative, possibly, right? However, if there is an even power in the factor, it can bounce. Right? It won't actually cross. If the power is even, it just bounces off the graph. That's the way it works. So let me draw my axes here. This is going to be pretty rough. I'm not really caring about, like, so here I was trying to be somewhat careful about the y scale. I don't care at all about the y scale, and not too much about the x scale either. I'm just trying to get a rough picture. So here's minus 6. Minus 3, 2, and 4. I'm more interested in these numbers being separate so I can see where they are than anything else. 8. So I put my critical numbers in order, and then if we plug in a point far, far to the right, it's easiest to think about because what's that going to do? Like what happens if you plug in 9? It's going to be positive, right? You can see that. So that means that the graph starts up here somewhere, right? And this is a linear factor, which means that the graph crosses there. So the crosses, right? What happens at 4? See, at 4 it bounces. So if you think about that, what that means is it has to come back up, right? And it has to bounce off 4 like that. And then what? It goes through 2, which means it's going to have to do what? It's going to have to turn around. And then, what's it do? It has to cross through x through minus 3, so it's got to turn around again. And then it bounces. Bounce. There we go. Bounce. Now, is this a careful sketch of the graph? No. But does it allow you to answer that question in the homework? Absolutely. How many local minimums does this function have? Yeah, 1, 2, 3. There's 3 local minimums. And how many local maximums? 1, 2, 3. And there's 3 local maximums, as it happens. And by the way, another sort of quick check on whether or not it makes sense. If you look at the overall degree of the polynomial, it should sort of look like that kind of thing. And so what I'm trying to say is this is 2 plus 1 plus 1. So 2, 3, 4, 6, 7. This is like a 7th order polynomial. So if you could take this and zoom way, way on out, if you zoomed very, very far away, what would this look like? From like really, really far away, this graph would just kind of look like this. Which is what I expect because it's overall odd degree with a leading coefficient, which is positive. So just like a double check on whether or not my graph kind of makes sense. I think it does. If the overall degree is even, it should kind of look like a big bowl. It should either have both ends going up or both ends going down, depending on whether the coefficient's negative or positive, the leading coefficient. But if you understand this, you ought to be able to do that homework problem pretty easily. Do you see what I'm saying? Okay. I think the first time I learned about the bouncing, I was like, what? But that is how it works, right? I mean, what's the fundamental example of that? How about just y equals x squared, you know? What's y equals x squared look like? Parabola, right? What's it do? Yeah, it bounces off 0. Right? In contrast, y equals x looks like this, right? Y equals x cubed looks like that, you know? So even power, it bounces, right? And x to the 4th would be the same, right? It looks kind of the same, more like goalposts, really. But even powers bounce, odd powers cross. Something to remember. Or put on your sheet, right? Okay, so I'll shut up. You guys have questions, yeah? Oh, I think I just failed to, although almost everyone's here. I should. Oh yeah, of course, of course. Would you like me to talk more about how to find the domain of a function? We should talk about that, right? How do we find the domain of a function if you're given a formula? What are the, so given formula, f of x, we look for trouble with what two things? The one is the square root of negative. Square root of negative number, that's trouble, right? And the other thing is divide by 0, right? Got to watch out for those. That's basically what what we're looking for. There's another thing to look for at the end of this course once we talk about logarithms, but we're not there yet, right? So let's look at an example. If I had f of x equal to the square root of, let's say, x plus 3, I could ask what's the domain of this function, right? So what do we need? We need x plus 3 greater than or equal to 0, because we need the input to be non-negative, and that gives us what? Yeah, x greater than or equal to minus 3. So in interval notation, that's minus 3 included to infinity. There you go. That would be the domain of f. So let's see here. Let's look at a different example. How about, what if I have f of x, g of x rather, equal to the cube root of 3x minus 7? What's the domain of this? See, that's what I'm trying to tempt you to think, but that is not the case. Why is that not the case? So let's think about this for a second. If you think about x squared, right? We turn that on the side, we get this, right? So here's y equals x squared. Here's x equals y squared, right? Is that a function? It's not, right? So what do? We chop this part off, right? In other words, this top part is y equals the square root of x. So that's actually the inverse function to not all of x squared, but just the right half of x squared. It's the inverse function to that, as it turns out. Because you can take this and flip it over the line y equals x, you'll get the top half of that, if I make my graph right. So square root of x is the inverse function of y equals x squared for x positive. But something neat happens with cube. With the cube, right, here's y equals x cubed. What happens when you flip x and y, which is what you do to find the inverse graph, right? It just turns it on its side. It looks like this, right? That's x equals y cubed. But the thing is, it passes the vertical line test. So you could say y equals the cube root of x. My point to you is the cube root of x has it's got no fine print. Like the cube root of x, we can input negatives. What's the cube root of minus 8, for example? I always give this as an example. Cube root of minus 8 is what? What's that? I heard a what? I heard a 2. But is that right? If it was 2, that would mean that 2 cubed equals to minus 8. But this is not true, right? Yeah, the cube root of minus 8 is just minus 2. In other words, the cube root of a negative number is negative, as you can see from this picture up here, right? You take the cube root of a negative number, you're down here somewhere. So all I'm trying to tell you is if we're taking a radical where the index here is an odd number, there's no strings attached. It could be, the input can be whatever we like. So what that means is that the domain of G is all real x. I'm telling you this because there's a problem in your homework where I'm tempting you to make the mistake that I thought you guys would make. And you're not the first, right? I've talked to like 3 or 4 different students in office hours, and most of them also thought that the cube root had to have a positive input, right? And I'm sure I thought the same when I took this course, But in fact, since the cube root can take anything, the answer here is just minus infinity to infinity. What if we did f of x plus g of x? What would the domain be for that? Well, first of all, what's the formula? Square root of x plus 3, right? Plus the cube root of 3x minus 7. How do you find the domain of the sum? When we talked about this, we said we intersect. We take the intersection of the domain of f and the domain of g. So what happens when you take the intersection of everything with that? It's still just that again. So this has domain. The domain of f plus g in this case is just minus 3 to infinity. Let me show you another example that's sort of related to this, but a little bit different. I think it'll help you. I'm going to get away from this cube root example because it's too, well, I guess I could, oh fine, there's one thing I could do. How about, well, I can do one more thing with that cube root example. How about if I look at h of x equal to 1 over g of x, where g is what I gave you over there, right? So what would that mean? The formula for that would be 1 over the cube root of 3x minus 7, right? What would the domain for g of x, what would the domain for h be now? We're not worried about taking the cube root of a negative number. That's not a problem, right? But we do need to worry about division by 0, right? Can the cube root of a number be 0? I mean, it can, right? Look at the graph of the cube root function. The graph of the cube root function, I'll draw it again here. The graph of the cube root function looks like this. Can the cube root be 0? I mean, absolutely. Cube root of 0 is 0, right? You could try your calculator. Plug in third root of 0, see what happens, you know? So what do we need to worry about? We need to worry about 3x minus 7 equal to 0, right? If 3x minus 7 equals to 0, then have division by 0. And that's a problem. So this is what? 3x equals to 7. In other words, x is equal to 7/3. So the domain of h is, we could say it's x, such that x is not equal to 7/3. How would I write that in interval notation? And you take the whole real line and just delete 7/3, right? What's that? Don't include it, right? Minus infinity to 7/3, excluded. Don't let it in the party. 7/3 to infinity. There you go. That's the domain. What have I done? I've done something. This example is not that funny. There's something else going on here. You're not going to tell me, are you? No? Processing. Huh. Seems suspicious. Here, let's look at this one. What if we had f of x equal to the square root of 3 minus x and g of x equal to the square root of 2x plus 2? Can you find the domain of f and the domain of g? Now we got square root, so it's not a trap. We need the input to be non-negative, right? So we got to solve 3 minus x greater than or equal to 0. In this one, we've got to solve 2x plus 2 greater than or equal to 0. See, what's one of the good things about this course is we're sort of automatically reviewing some of the stuff on test 1 as we go on, right? Because we keep using it, you know? The nature of math, isn't it, here? So 3 is greater than or equal to x. I add x to both sides. Yeah. And this gives me what? 2x minus 2, yeah? So, of course, this we could also write as what? X less than or equal to 3. And this we could write as what? Well, or yeah, I think x greater than or equal to minus 2 over 2, which of course is equal to minus 1. So the domain of f is what? X, 3 included. All right, I'll take that. And how about the other one? What's the domain of g? Watch out. Yeah, negative 1 included to infinity. So what if we add these functions? What's the domain of the sum of the functions? F plus g, what's its formula? That's easy. Nobody has a problem with the formula. It's square root of 3 minus x plus the square root of 2x plus 2, right? We all got that. That's money in the bank, right? What's the domain of f plus g, though? What did we say when we talked about this in class? We said that the domain of the sum, we intersect the domains of the functions we're adding, right? Well, let's draw a picture. So we've got minus 1, right? We've got 3. And if I draw the domain of f in blue, what's it look like? I'll draw it below the line just so I can you see both of them. So the domain of f looks like this, right? And the domain of g, on the other hand, yeah, just the opposite. It starts here, but it goes that way. In order for us to add these two formulas together, we need for both formulas to make sense, right? So we intersect the domains to find the domain of the sum. Intersect. So it has to be, both have to be true. No, not negative 1. If I'm past 3, the red one doesn't. If I'm past 3, the blue one doesn't make sense. The negative 1 to 3. Yep. And they're both included, right? Because there's no trouble with either minus 1 or 3. It's just that at minus 1, the second term is 0. And at 3, the first thing is 0, right? So we get to include both endpoints. There's no trouble there for this example. What if we looked at f over g? How would that change things? So it's square root of 3 minus x divided by the square root of 2x plus 2, right? What's the domain now? So we still need both formulas to make sense, right? So we already know that both formulas make sense. F of x formula and the g of x formula, they make sense as long as we're in that -1 to 3, both of the ends included, right? But now we need to worry, because we have what? We've got division by that formula. When is 2x plus 2 0? If x is -1, 2x plus 2 is 0, right? So that means that we have to exclude -1 in this case. So we exclude -1 because we have division by 0 there. What if we had g over f? You're like, hasn't this example done enough? So there we'd have square root of 2x plus 2 divided by the square root of 3 minus x, and the domain of g over f, what's that equal to? -1 is included this time. Exclude 3. Because this time we have division by 0 when we set x equal to 3. All of these questions about domain of function, you can figure out the answer by simply looking at the formula and asking yourself the question, what x caused division by 0, or what x caused me to have the square root, or an even root, more generally, of a negative number. If I have either of those features, got to rule them out from the domain. That's all I got to say about that. I think these will help you do about 3 or 4 problems in the homework. Because there's a multitude of questions in your homework which are basically about this particular corner of the math. You guys got questions? You must have a question. No? Can we leave? Hey, I submitted a law to another class. Have you guys ever heard of Godwin's law? Any internet argument within a finite number of iterations will devolve into an argument about Nazis. Like, you want an example of evil, right? So at some point or another, you're going to liken the other side to being a Nazi, because they're the ultimate example of evil in our time, pretty much, right? Sorry if you're a Nazi, right? It's not something you usually need to say to people, right? Like, as far as I know, no Nazis in here. But I think there's a law of classroom discussions. Any classroom discussion left to its own volition will degenerate into a discussion about leaving class within about 2 iterations. Like, I was discussing this with another one of my sections. I think it's a universal feature. If I leave the discussion open, it will soon degenerate into let's just leave class. And so I think what Heaven is about to say is, like, why are you fighting it? Like, it's the will of the people. This is a democracy, right? See, that's where it's leaving classes. So he's bringing it together. He's saying leaving class is better than being a Nazi. Yeah, I was not necessarily trying to say that if you want to leave class, you're a Nazi, but that is a ridiculous and fun argument. But yes. invertible functions. Let's talk about that. Heaven's like, no, the previous conversation was better. See, but the reason you don't want to leave class is because the more times we don't leave class and the more times you learn the material, the closer you get to the point of never coming back to this class again, which is really what you want, right? So, man, that brown marker doesn't quite erase. All right, so inverse functions. So first of all, to graph, how do we graph inverse function? Basically, if I have a function, you know, oh, that's bad. Let's see here. Try something else. Let's see here. Suppose I have, I'll just do, come on. Sorry, I have lack of imagination here at the moment. Like that. If that was my function, if that was y equals f of x, then I need to just take some points on it. Let's suppose that that's minus 3, 0. Let's suppose that that's 0, 2. Let's suppose this guy up here is like 1, I don't know, 5, right? And I'll take another point right here. What's that one going to be? Maybe 0.5, 3. All right. I'll take those 4 points, and I'll show you what corresponding points they give us on the graph of the inverse function. So it's very simple. All you do is you take the x and y coordinates of the points and flip-flop them. Now, graphically, that corresponds to, turning the graph on its side like I was doing a minute ago for y equals x squared and y equals x cubed, right? For this one, so you guys help me out, where would, this flip-flops to what? 0 minus 3, which is where? Down here, something like that. And, yeah, 2, 0. If I was in my picture, not quite right, but there it is, as best as I can do. And 3.5, so it's like here somewhere. And 5, 1, right? It's like here-ish. And then you can kind of connect the dots like that. So there would be your y equals f inverse of x graphically. And so how do you know, what function can you not find an inverse function for? What feature do we need for a function to be able to find the inverse function? Why was it that x squared had trouble? Right, it doesn't pass the well, this passes the vertical line test, right? That's fine. F of x equals to x squared. If I was to do this thing we just did, flip the x's and the y's, what happens? You get a parabola that opens sideways, right? You get this thing is what you get. And the equation of that is x equals to y squared. But the trouble is, that's not a function, right? The red graph is not a function. It fails the vertical line test. The reason it fails the vertical line test is because the blue graph there fails the horizontal line test, right? I mean, that's basically what happens, is that what was a horizontal line in the original story, when you flip it, becomes a vertical line for the new transformed graph. And so if that vertical line intersects two places, not a function, right? So that's why we need the original function to pass the horizontal line test. Otherwise, when we flip the function, we're not going to have a function. So one of your homework problems is like, here's a picture of a possible invertible function. Graph the inverse if you can. If you can't, say why not. One of those doesn't pass the horizontal line test. So if it doesn't pass the horizontal line test, it's not invertible. You can't graph the inverse function because it doesn't exist. I mean, you could graph the inverse relation, it's called, but it's not a function. So, all right. So that's, Mo, that's the graphical answer to your question about inverse functions, but you want me to talk about how to find the formula also? All right, so suppose we have a function and we know it's invertible, right? How do we find the formula for the inverse? So for example, I'll run down, I'm pretty sure this is invertible, 3x over 2x plus 8. I'm pretty sure that this function's invertible. How would I find the formula for the inverse function? What's my step number one? I write y equals to the formula. My step number two is to solve for x. Solving for x is going to look different for different problems, right? But you need to use the laws of algebra that you've learned or that you've recently remembered, right? So what are we going to do? I suggest, well, first thing I'm going to do with that is I'm going to multiply both sides by I'm going to multiply the denominator to the other side, basically, right? I'm going to have, that's y times 2x plus 8 equals to 3x. Are we on board with that? Then I'm going to distribute, and then I'm going to get 2xy plus 8y equals to 3x. I'm solving for x. That means I want to make all the x's go together. So you kind of got two choices. You can either bring all the x's to the left or all the x's to the right. What do you guys want to do? Go to the left or go to the right? Huh? Democrats. Let's see here. I'm sorry. I'll stop. This is, exciting presidential debate today. You guys know there's a debate, presidential debate tonight?
Yeah.
Should be very exciting. I can hardly wait. Oh, yes, x. So 2x. Oh, I shouldn't use this. This green marker didn't show up good. So 2x. So we'll go to the left here. 2xy minus 3x equals to minus 8y. I got to bring the y to the right then, right? And I can factor x out, right? This gives me x times 2y minus 3. And then I can, right, finishing blow. See here, x equals 2 minus 8y divided by 2y minus 3. Hey, fun fact, if you want, you could rewrite this as 8y divided by 3 minus 2y, if you prefer. You can pull the minus downstairs and flip it. It doesn't matter. Either one is fine. So what is f inverse? So f inverse of y is 8y over 3 minus 2y. Of course, you could also use the other